biology as well as physics. So I loved solving problems in physics and math, and at the same time I was very fascinated with what's going on in the human body and how people create new drugs to solve different diseases. So, but up until recently, I couldn't bridge these two fields together and help one another from each field. So today I'm going to talk to you guys about how I could do it. And before that, I'm going to give you a little bit of background about myself. So I am from this part of the world that is restricted in the map. So if any one of you can guess where I'm from, exactly? India is very close.
Nepal.
Huh?
Nepal.
Nepal. That's the first time I'm hearing that. No?
Thank you.
Any other guesses? No. Okay, I'm from Sri Lanka. Sorry. So it's an island very close to India. So a little more facts about it. And it's a very geographically very small place. And the one good thing that I had in Sri Lanka in terms of education is that they would let the top 5% of the student population have free college education. So at that time it was very competitive, and like looking at you guys reminds me how much stressful I was facing those exams and stuff. So and also I was born in a place where it's shown with the pink dot, and I moved to the capital, which is Colombo, to do my college studies after I got through the exams. So the distance is about 60 miles, not so much, but that was the furthest that I've moved from one place to another before I came to US. But that was also with my family. I wasn't living by myself. So Sri Lanka is like, it's the culture and the family that I'm from. We are very close-knit, and I really valued the fact that I was able to be with my family throughout the whole time that I was living in Sri Lanka. So my father, he's a pharmacist, so we were literally living on top of, like, on the second floor of where we worked. So I would see a lot of medicines and the patients who come in to take those medicines, and the biology part was like built into my life from my family background. And also I really valued the fact that I had a lot of freedom to study what I really liked, and I like to write plays and act on plays, and here I'm acting like a scientist. Well, not so much. This is sort of my background, and coming from this kind of family, and when I was about your age, because of the system, the education system in Sri Lanka, so this is what I really like doing. So I like doing biology and figuring out how to fix things, like how to put things together, how to build things. So like growing up, those were my hobbies, and thinking about how to like employ my fascination on building stuff to like human body. What can I do there? Like, can I study biology and figure out how to make new things? How to solve problems in biology, like I was solving problems like math problems on paper. So I grew up liking these things, and because of the education system in Sri Lanka, when I was about your age, I had to pick one out of these 4 streams. For example, if you were doing like finances, you have to skip everything else. So it's like you get to only study one stream. In contrast, you guys have this system, like the college education system, which I feel like you guys are really fortunate to like study a lot of like broad subjects, and then study it for like a couple years and decide what you really want to do. So this was one thing that I really didn't like at that time, to make such a big decision while I really liked biology and physics, and it felt like a really burden to pick one out of the other, and then having the thought of like, oh, I'm not going to study the other one ever again in my life. Is that what's going to happen? So this was like one big question that I had to figure out at that age. And then again, obviously, I went with what I thought right at that point, which was physics. I liked building stuff and figuring out, solving problems. So I went with physics and then studied physics and math 4 years in my college at University of Colombo in Sri Lanka. And it was great. It was really nice to know a lot of new techniques, and I got introduced to like systematic research, how to collect systematic data, how to interpret data, those like basic practices, and also like taking higher level courses to figure out the math you need to solve physics problems. But then again, like back in my head, there was always this thought like, oh, I'm not studying the biology anymore that I really like studying. And like it really hits me when some of my relatives get sick, or some of them made with accident and broke their leg or whatever, and then I feel like, can I use my knowledge in building stuff to figure out how to fix these kind of biology problems? And by the end of the college, I realized that if I came to US, there are like so many labs, so many institutes that lets you study physics and biology together, and even let you like do research on them while studying both of these together. So this was really like giving me back the hope of I get to study biology again, and maybe I can solve some problems. So because of that, I decided to come to US, and literally like being in a flight one whole day and leaving my family behind. And also like these practical problems like living all by myself, maintaining the house and cooking, and same time studying for the first time in my life. So, but I felt like, well, this is my first chance of getting to study biology, getting to like solve problems in human diseases, and maybe like figure out how new drugs get delivered in the body. So this was the motivation to take this step forward and come to US and study what I really like studying. So I went to University of Akron to take some graduate courses in master's level. And then I was introduced to Brandeis by a professor there. And I came to Brandeis, joined Fraden Lab to do my PhD. So in Fraden Lab, I got to study proteins, which is like big part of biology that you really like to engage when you try to figure out how the human body works. And so because of my lack of biology knowledge, I had to go back and take a lot of biochemistry and biology classes, which I really enjoyed. It was like coming back to something that I lost a couple of years ago. So after joining this lab and after getting my PhD, from that knowledge and the skill set that I had from physics background, I could really combine these two to do the kind of research that I'm doing today, which I'm really excited to talk to you guys about. So this part of my talk is about what my current research looks like. So what you're seeing here is inside the cell, there are so many proteins, and I'm going to concentrate on two different proteins. The protein that is walking, like you see this guy is holding up his feet on top of a vesicle, which is cargo. For example, it's walking on a track, which looks like this tube. It's walking on that track, carrying a lot of cargo. So this is how proteins move one thing to another place inside the cell. So from my physics background and from my fascination of building things, what I wanted to do is like take these pieces and then see if I can make some materials that I can really take advantage of. So what I do, for example, is that I take this walking guy. So it has 2 feet, the blue 2 feet, let's say. And then I put another protein which acts like a glue, which is the yellow circle here. And then I put another walking protein on top of it. So this new complex, we call motor complex, it has like 4 feet on the opposite side. So it's basically something like this, right? So, and then I want to ask the question like, what would this do if we give it a track? You remember from the movie there was a track these guys were walking when they had only 2 feet, right? So what if I gave them 1 track or 2 tracks or more tracks? What would this new complex do? Because this is building things from biology. And can anybody guess what it would do? So it's something like this. So if I can have somebody come in and help me explain this. Any volunteers? So, yes?
I'll do it.
Can you come in?
Just do it.
Yeah, let's do this. So I'm going to take my arm. So these are going to be the tracks, right? So in a rail track, there is a starting point. Let's say this is my starting point and this is my destination. So if I keep my tracks like this, it's one configuration. If I keep my tracks like that, it's a different configuration. So can you be the walking protein complex, the motor protein complex, which is in between? So your fist, you can take your fist. So his fist is going to be something like this. So we are going to simplify this. This is what we do in physics. We always simplify things. So this is going to get simplified like that. So his fist literally has like 2 feet up here, 2 more down here, right? So you're going to come in between my arms, which are tracks, right?
Okay.
So you know you can only walk from starting point to the destination.
Okay.
There's no walk behind, okay? You can't walk backward.
Okay.
That's the only limitation you have.
Okay.
All right. So imagine I keep my tracks like this. So this is starting point, this is the destination.
Okay.
And also keep in mind that you have 2 sets of feet,
Feet out.
right?
Okay.
All right. So what do you want to do now?
Go that
If
way.
you come in between, yeah, what do you want to do?
I'm gonna walk that way.
Yeah.
I'm gonna use my other feet and walk back this way. And then so forth.
Why do you walk back? No, I put a restriction. You can't walk back. You can
Okay.
only walk towards the
Okay.
destination.
Okay, I walk that way.
Okay.
Okay.
And at the end, what would happen?
I wouldn't be able to go back.
No, and you fall off, right?
Yeah.
And focus on the tracks, guys. What would happen to the tracks?
They drift apart.
They drift apart. If it came in like that, it would fall off. And the tracks are not moving at all, right? What if I keep my tracks like this? What are you going to do now? So this way is one destination. This way is another destination. So the feet that you have up here would see one destination, and the other feet would see another destination, right?
Yeah.
So what would it do?
I'd walk that way, and then I'd use my other feet to go this way. Because the tracks go that way.
Right? So he's sort of stuck here, and the tracks would be moving that way. Do you guys see it? So this is motion, right? So we built something from 2 sets of protein.
Okay.
Thank you. So we built something from 2 sets of proteins, and in one configuration, the tracks were stationary, or tracks were like stuck. The protein would fall apart. And in the other configuration, we could make a movement, right? We could generate some movement. So this is what I'm going to leverage. So when I put these guys together like that, there will be tracks coming in this way that can move. And if I put a lot of these things in a high concentration, this is what it's going to look like. So what you're seeing here, the white strings are those tracks. So I put a dye for you guys to see it, because they are very small particles. So the track protein is not labeled, so you can't see it, but they're inside this. So because of these tracks would move and create a motion, right? So you guys know, like, we can't really get any work done, or we can't see light without electricity, for example. We can't move something without putting a force on it. But these guys, they move by themselves, right? So we created something out of only single proteins which are in a cell, and then we created a motion. We created a new material that can move by itself. So this is what fascinates me by combining physics and biology, like create work out of some biological components that I didn't know how to do until I came here and started doing research in Brandeis. So the next fascinating questions that I like to ask is like, what would happen if I put this in different shapes? For example, what do you think happened if I put this in a circle or a disc in a container? What would these guys do? Yeah? Okay, let's see what it's going to do. I think you're right. I heard you saying spin, right? Yeah. Okay. So this is a circle. And look what it's doing. See, it's pushing material inside. And then it keeps rotating. Right? And it does it very regularly, like a clockwork. You know, like it keeps pushing material, circle it. And it keeps doing it for a long time. And so this phenomena, or this behavior, you take some material, put it in a circle, and you see something really different. And these are like very rich systems that we take out of biology, use our physics skills to study, and make new material. And you can go crazy with these kind of materials. So if I have to put this inside a donut, what do you think is going to happen? So it's going to keep circling inside the donut in one direction. And sometimes it picks the direction randomly and keeps moving inside the circle without any external energy, right? So, yes, we can maybe power up Iron Man's heart like this at some point. So there are so many opportunities in this kind of research field. Like you can use this kind of work or knowledge to make like new drugs. What if we can use this material to deliver drugs inside our body from one place to the other? And what if we can like create energy, get some real work done out of these motions, and we convert these motions into something like actual work to, for example, move one like payload to the other direction. So these are the kind of questions that I like studying and trying to answer using physics and biology. And I really enjoy having this opportunity to come into like a place like Brandeis and doing this kind of research. And I really want to emphasize you guys that it's like literally on your backyard. You guys can come and visit our labs and try to think about what you see and what you really like doing in your college. Because unlike me, I had to come I had to travel one day to see what's gonna happen. Like I didn't know before. I didn't have the chance to visit labs and see what they do. So it was almost like a blind decision, like what kind of research that I will be engaging in. But you guys can always visit our labs and see all the cool stuff that we can show you guys to decide what you really like doing. So with that, I think I'd like to close it, and I'm going to show you last slide, what kind of
Does anybody have any questions for?
If you have any questions,
I have a question. What is the food that do you have to? Do the
Yes.
proteins just go on forever, or do you have to?
Yeah, so these things can move by itself until we supply food for the protein, right? So the protein walk, for you guys to walk, you need energy. Same for protein. So you guys have to do work, and we need to put them. We need to give them the food that they want. So it is called ATP. So we put that chemical inside these mixtures when we start the experiments. So it consumes the food, the proteins, the walking proteins would consume the food to make the motion happen. Yeah?
What would happen if we mutated?
What
would happen to these proteins if they mutated?
So this protein is already sort of mutated because as I explained to you, I put two guys together, right? So it's not the actual protein which is inside the cell. So using physics and engineering skills, we sort of mutate the original protein and put them together. So this is what happens when you do the re-engineering to the protein.
do have a question. Can you mutate, just to follow up on this? Like, is it possible that if you changed part of the protein of the walking kinesin, if you changed like one amino acid or two amino acids, would that, and not to create your motor complex, but just starting with the kinesin, if you changed a couple amino acids, could that affect its ability to walk?
So it really depends like which part is important for the walking. So that's also like when you study about proteins, you try to figure out what they do, and then you try to relate what they do to how they look like. For example, we say structure and function. So if we go and modify or mutate the parts that it wants to walk, for example, then it would disable the guy. But as long as we keep that function preserved, it can always move. So.
And that's the bell. Thank you guys so much for coming. Thank you, Achini.